In this episode of What's the Big Idea, we're going to be talking about the extremely important and big idea of energy and the related law, the conservation of energy. And energy is one of these terms that we use in everyday language, and it's used rather loosely. We talk about conserving energy, and these are very important topics for very practical reasons. But as is often the case, physicists have very particular meanings of what they mean by the word energy and what they mean by conservation of energy. So, in this episode of What's the Big Idea, we're going to try to give sort of a big picture overview of what we mean by energy and the conservation of energy. Well, one physicist who thought during his career a lot about energy was the great Richard Feynman. And Feynman was not only a deep thinker, but he was also a skilled explainer. He could make complicated ideas accessible. And here's his take on the law of the conservation of energy. He says there is a law called the conservation of energy, and it states that a certain quantity, which we call energy, which does not change in the changes that nature undergoes. It is a most abstract idea because it is a mathematical principle. It says that there is a quantity that does not change when something happens. It is not a description of a mechanism or anything concrete. It's just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the same number again, it is the same. And I like this quote because it combines, two sort of um, seemingly contradictory statements about energy. One is that it is sort of abstract and, in some sense, inaccessible. And yet, in the end, the description is that it really sounds very simple. It's just some number that we calculate, and it never changes. So that is a very concrete thing that we can do, and is, in some sense, very simple. And we'll see in our discussion that this law of the conservation of energy actually does make a lot of problems in physics much simpler to deal with. Now, another great physicist who thought a lot about energy in the course of his life was Albert Einstein. Here's a picture of Einstein thinking about energy. And there's a famous sort of anecdote about Einstein, which I'll tell here. Um, Einstein later in his life came to live in Princeton, New Jersey, and he and his first cousin and second wife, Elsa, lived on a nice house in Mercer Street in Princeton, right near the university. And Einstein's accountant was a fellow named Leo Mattersdorf, and Mattersdorf went over to Einstein's house to prepare Einstein's income taxes one year and have lunch with Albert and Elsa Einstein. And during the course of the conversation, Einstein remarked to Leo Mattersdorf, "The hardest thing in the world is to understand income taxes." And Mattersdorf said, "Well, actually, for me, the hardest thing in the world is your theory of relativity." And Einstein said, "Oh, no, that is easy." And then Elsa said, "Well, for you it is." So anyway, the moral of that story is, I think, severalfold. One is that uh, Einstein's thinking about energy was not so easy for many people to appreciate, but the idea that income taxes were hard is an interesting notion because what makes income taxes hard for people is not anything sort of deeply conceptual. It's just that there are these rules that you got to obey, and the rules can be a little bit complicated, and it's more or less of an accounting problem, really. So it's interesting that this story involves Einstein's accounting, because when you deal with energy, a lot of it really is just careful accounting. And if you add up the books properly and apply the laws of conservation of energy, it's really, in the end, not so complicated. But you just have to keep the rules straight. So what makes your income taxes hard is not a deep uh, complexity, but rather just some complications about the rules. And we'll see that when we deal with problems involving the conservation of energy, Often the sticking point is just getting confused about how to do the accounting. It's really not a deep problem. So it's one that if we're careful about, we'll be able to deal with without too many problems. So the law of conservation of energy is really one of the most important ideas in physics, and it is really central to the discussion in Wolfson's chapter 6 and 7, which I think are very well written. But I have one significant criticism is that I think Professor Wolfson is guilty of what I would uh, refer to as burying the lead. Those journalists amongst you know that when you talk about burying the lead, uh, the lead is the introductory paragraph of a story, and burying the lead means you start off with sort of things of secondary importance, and you don't get to the main idea until well into the story. And Wilson doesn't really explicitly talk about the concept law of conservation of energy until well into chapter 7, the second of these two chapters. So I wanted to try to correct that by putting the law of conservation of energy right in the lead paragraph, and just give this big overarching view so that as you read through chapter 6 and 7, especially for the first time, you'll have an idea of where we're heading is and what the big idea is. So to talk about conservation of energy, let's consider a specific uh, case, a simple case of a system consisting of the Earth and a ball, say a soccer ball, located not right resting on the Earth, but some height above the Earth. Let's call this height h. And as I said, when you deal with energy, it's ultimately really an accounting problem. So you've got to be uh, go out of your way to be as clear as possible about what the rules of the accounting are. And in all of our energy problems, I'm going to insist that you get into the habit of identifying what we're going to call the system. The system in this case consists of just the ball and the earth. And we're going to identify the system, and we're going to draw a dotted line around our system. And anything inside the dotted line is part of the system, and anything outside the dotted line is not part of the system, it's part of the surroundings. And so in the current discussion, we're going to assume that our system is isolated, isolated system. And by isolated, we mean, by definition, there is no interaction with the surroundings. Okay. And in this case of an isolated system, um, the law of conservation energy applies, and the law states that when you have an isolated system, the energy of the system will not change. So we'll write that succinctly with the following notation. E system refers to this number, which Feynman talked about, the energy of the system. And if the system is isolated, then the energy of the system will not change. So this thing that we've just written down is a concise statement of the law of conservation of energy. And it applies again only to isolated systems. So, what happens to the system if we let it go, if we just let it evolve over time? Well, if the ball is hanging there at a height h above the Earth's surface, you know it's not going to stay there. There's a gravitational force between the ball and the Earth, and they're going to fall towards each other. Although, of course, because the Earth is so much more massive than the ball, most of the motion is going to be due to the ball. So, what does that mean for the this law of conservation of energy? Well, the way we're going to end up describing this is initially all of the energy in the system is going to be in the form of what we're going to call potential energy. Uh, and then as the ball falls to the earth, uh, the potential energy in the system is going to decrease But the ball, due to its motion, is going to require another form of energy called kinetic energy. And when we add up the two forms of energy, we find that the total remains unchanged. And that's what we mean when we say that energy, overall energy, is conserved. If you take into account all the different forms of energy, the total energy of the system uh, does not change over time if it is an isolated system. Well, what if there are interactions between the system and the surroundings? For example, suppose we know that we're surrounded by other objects in the universe, things like the sun and the moon, and there are going to be gravitational interactions. And so there are going to be interactions with the surroundings. What do you do then? Well, there's a more general form of the um, law of conservation of energy, which we're going to refer to as the energy principle, which allows you to calculate how the energy of the system will change when there are interactions with the surroundings. And the way we're going to write this more general form, which we call the energy principle, is to say that the change in the energy of the system can be calculated by calculating something called the work done by the interactions with the surroundings. And Professor Wolfson calls this work done by the surroundings, by this external world, he calls it W sub EXT, and that's what we'll call it also. So this is our energy principle. And the word principle is chosen to indicate that it really is a very fundamental idea in physics. And just a couple of final comments. One is that um, for all of the examples that we're going to cover in this course, the energy principle is really not anything fundamentally new. It can be derived from Newton's laws of motion. So in that sense, it's not a new statement. It's just derivable from Newton's laws, but it is simpler to deal with. You'll notice, and from our description, that we're just calculating numbers here. These are scalar quantities, whereas Newton's, say, second law of motion involves vectors. And it's easier to deal with scalars than vectors. So the energy principle is going to make life a lot easier for dealing with certain kinds of problems. And then the second and last point that I'll make is that we've neglected something important in writing down the energy principle, and that is things having to do with thermal effects or heat. So a more complete statement of the energy principle would have an additional term on the right here, which is called Q, and that has to do with energy entering or leaving the system in the form of heat. But if you want to learn about those kinds of problems, you'll need to take Physics 205, which is all about thermal physics. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.